Okay, so it's a great pleasure to have Yasunori Lee. He's going to tell us about revisiting WZW terms.
Okay, so then let me start. So thank you for the introduction. So first of all, I would like to thank Nawata-san for inviting me to give a talk in this wonderful seminar series. Today, I'm going to talk about our recent work on Wess-Zumino-Witten terms, which is based on this paper with Omori-san and Tachikawa-san. So let me begin with the old story about QCD. QCD is an SU-NC gauge theory coupled to NF fermions in fundamental representation of the gauge group. So when these fermions are massless, the theory is invariant under SUNF left times SUNF right flavor symmetry, which acts on left-handed fermions and right-handed fermions respectively. As is well known, for small enough NF, QCD is asymptotically free. And as one flows down to the low energy, the theory becomes more and more strongly coupled. And at some point, the fermions form bilinear condensates. And correspondingly, the flavor symmetry is spontaneously broken down to SUNF diagonal subgroup. As a result, the low energy effective theory is believed to be described by the nonlinear sigma model, where the fundamental degrees of freedom are the Nambu-Goldstone bosons associated to this spontaneous symmetry breaking. So that's the basic description of the theory, but one important fact which will be relevant to our story is that the flavor symmetry in the UV is chiral. So therefore, if we turn on the background gauge field for this flavor symmetry, it immediately gives rise to familiar triangle anomaly for NF larger than or equal to 3. This means that we are not allowed to gauge this flavor symmetry. Such obstruction to gauging the global symmetries is called a 't-Hooft anomaly, and it is known to be conserved under the Auger flow. So we expect this 't-Hooft anomaly of the flavor symmetry in the UV QCD to be somehow reproduced in the IR nonlinear sigma model, but one is led to wonder how that's possible, since apparently there are no fermions in the IR. The answer has been known for decades. So the 't-Hooft anomaly of the flavor symmetry in the UV is reproduced in the IR by a certain topological term called Wess-Zumino-Witten term. So it is defined as an integral over an auxiliary 5 manifold, W5, which is bounded by the original space-time 4 manifold, M4. And the integrand, gamma 5 sigma, has a following form, where this sigma is a map from the auxiliary W5 to the sigma model target space G over H, which is SUNF in this case. So this sigma is namely the Nambu-Goldstone bosons suitably extended from this spacetime M4 to the auxiliary W5. So this is the definition of the Wess-Zumino-Witten term. But one immediately finds that there's an obvious ambiguity in this definition, in a sense that this W5 is not unique, and there are many different choices of W5 in general. So if the value of the Wess-Zumino-Witten term depends on which W5 we take, then the Wess-Zumino-Witten term might not be well defined. So we want to make sure that such problem does not occur. Again, the argument is well known. So first, take an extension to W5 and take another extension to W5 prime. So the difference between these two extensions is equal to W5 and W5 prime with orientation reversed, glued along the common boundary M4, which results in a closed 5 manifold. Correspondingly, the difference between two Wess-Zumino-Witten terms on W5 and W5 prime is given by a Wess-Zumino-Witten term on this closed 5 manifold. Recalling that what actually matters is the exponentiated action. So we want this difference or ratio between these two exponentiated actions to be trivial. This means that the Wess-Zumino-Witten term on any closed 5 manifold must be 2 pi I times an integer, or equivalently, this gamma 5 integrated over any closed 5 manifold should be an integer. So let's check whether it is actually satisfied by looking at concrete examples. So the most familiar closed 5 manifold is probably an S5, the 5 sphere. I hope we all agree on that. So we start off with this case. Fortunately, the gamma 5 integrated over S5 turns out to be 1, which is an integer as desired. This is actually the case originally considered in the Witten's paper, where the spacetime 4 manifold was taken to be a 4 sphere. However, one can, of course, ask what will happen if we take more generic spacetime 4 manifold? Can we define Wess-Zumino-Witten terms on arbitrary spacetime with arbitrary sigma configuration on it? So to answer this question, let's next consider a less familiar closed 5 manifold, which is SU3 over SO3. This time, gamma 5 integrates to 1/2, which is not an integer. So for even NC, so integrality as a whole can be achieved, and correspondingly, the Wess-Zumino-Witten term is still well-defined. But for Wess-Zumino-Witten term to be well-defined even when NC is odd, we need something additional to remedy the situation.
How do you show this is 1/2?
You can explicitly calculate it. So
Okay, it's a group
yes, there's a
manifold, so it's okay.
yeah.
It's a concept model, that's why. Okay.
Thank you for asking. So one notable difference between these two manifolds, S5 and SU3 over SO3, is that while S5 can be equipped with spin structure, SU3 over SO3 cannot. So SU3 over SO3 is actually a non-spin manifold. It is further known that gamma 5 integrated over any closed spin 5 manifold becomes an integer. So we will see why this is so later in this talk by using some mathematical objects called Bordism groups. Oh, but anyway, so therefore one can deduce that we actually need spin structure to make Wess-Zumino-Witten term well-defined. This necessity of spin structure is indeed natural since the original UV-QCD contained fermions, whose existence already required spin structure in the first place. So in short, the spin structure saved the day and the case closed. However, this is not the end of the story. So there's yet another subtlety swept under the rug. So earlier, I said that the auxiliary W5 is bounded by the spacetime manifold M4. But for generic M4, it is not at all obvious whether there always exists such W5 in the first place. And in fact, it is known that a K3 surface cannot bound any one higher dimensional spin manifold. So even in this case, the K3 can be connected to another K3 surface by W5 like this. And the Wess-Zumino-Witten term on this W5 is still well-defined, since the difference between two such extensions is still given by a closed spin 5 manifold, as before. But it only determines the relative ratio between two Wess-Zumino-Witten terms for the boundaries. So, however, there's a way out. So the point is that the value of the Wess-Zumino-Witten term for trivial sigma configuration should be trivial. Then, for a given M4 equipped with sigma, if we can connect it to another four-manifold equipped with trivial sigma configuration, one can just define the Wess-Zumino-Witten term for space-time M4 here as an integral over this W5 times, times this Wess-Zumino-Witten term for this boundary, which is trivial, since the sigma configuration is trivial on this side. So one might wonder, oh, okay, fine, but given space-time M4 and sigma configuration, how do we know whether we can connect it to such nice manifold on the other side? But luckily, this information is exactly captured by another Bordism group, and one can indeed confirm that it is always possible to find a four-manifold equipped with trivial sigma on the other side in this case. So at last, the puzzles concerning the SU Wess-Zumino-Witten term are all solved for NF larger than or equal to 3. On the other hand, when NF equals 2, things are rather different since there is no tooth anomaly and gamma 5 also does not exist in the first place. Instead, there's an interesting twist due to the following fact. So consider the fourth homotopy group of the sigma model target space SU and F. So this group is trivial for generic NF, but when NF equals 2, it becomes Z2. This means that when we take the space-time 4 manifold to be 4-sphere, there are non-trivial sigma configurations corresponding to this non-trivial element of this Z2, which cannot be smoothly deformed to the trivial configuration. As a result, there's a room for a choice of weight for these non-trivial sigma configurations. So this is the weight term. And this bracket here denotes the equivalence class of sigma. So it takes value 0 for sigma, which can be deformed to trivial sigma configuration, or it takes value 1 for sigma, which cannot be deformed to the trivial sigma configuration.
Sorry, I missed the point. So dimension 3, how does dimension 3 play the role here? Dimension
So
SU2 is equal to 3.
So Wess-Zumino-Witten term is described as a cohomology class of this target space.
Yeah.
But the target space dimension is smaller. I mean, the Wess-Zumino-Witten term has degree 5, while this SU2 have dimension 3. So
Yeah.
you cannot have 5 form. I mean, yes, you cannot have 5 form for the Wess-Zumino-Witten term.
Then you get Z2 in pi 4.
Yes.
Okay. So this sigma is not the spin structure? So what's the sigma?
Sorry, sigma is not spin structure. Sigma is a Nambu-Gosson boson.
Okay.
Yes.
Okay.
On space-time and extended to auxiliary W5.
Okay, okay, thanks.
Sorry for the confusing notation, but okay, so where did I go? Yes, this weight term, yes. So this weight term is actually known to be equal to the ordinary Wess-Zumino-Witten term for NF larger than or equal to 3, when we think of this SU2 as a subgroup for SU and F. So we call this term discrete Wess-Zumino-Witten term. And believe it or not, this discrete Wess-Zumino-Witten term also can be captured by the same Bordism group which we saw in the previous slide. Thus, although the situations are very different depending on the number of flavors, one can describe ordinary and discrete Wess-Zumino-Witten terms in the SU QCD uniformly from the Bordism point of view.
So when you say here -1 to NC bracket sigma, I mean bracket sigma is the element of pi 4?
Element of, yeah, yes.
Okay.
So yes, if the sigma belongs to the trivial element in the C2, then it's 0.
Okay.
And if it belongs to non-trivial element, then it takes non-trivial element in Z2.
Okay.
So it's 1. Yes. And that's the end of the introduction part. So before going on to the main part, let me give a brief overview of today's talk.
Can I ask a question?
Yes, sure.
Sorry. So can I go back to the last slide?
This
So
one?
pi4 is a map from S4 to SUN.
Yes.
So here you in the bottom you allow M4 to be arbitrary.
Oh, sorry. You can later it is generalized to generic M4, but yes, it's yeah. You can think of this M4 as S4 here.
I see. So even for general M4, it's still a correct definition.
Yes, then and that will be captured by the Bordism group.
I see. Okay, thank you.
Thanks for asking.
One more question.
Yes, sure.
So this might be tangential to the direction that you want to go, but I just wonder, I mean, all these cobordism group, I mean, I thought they're for like a global topological property of the space-time. Is there, but on the other hand, for example, the Hooft anomaly matching, which is, you know, basically to compare the UV and IR theory, does not necessarily say concern about, for example, the very large scale of the space-time structure, but it might be more local. I mean, say concern is more about the local physics. You know, if you really just flow to the IR, you don't really flow to the galactic scale, but no, say still some say particle physics scale, which really does not really see the space-time topology. So in what sense? I mean, in other words, is there a more local way to think about how to extend the WZW term rather than, you know, have to really talk about the global topology of the whole space-time, maybe even after proper compactation? I think you know what I'm trying to ask, right?
I'm not sure what.
I'm just trying to say that.
Yeah, I'm not sure what you mean by saying local, but
you know, it's really about the, you know, the pion scales. I mean, say the distance scale set by the pion physics. It really should not say concern about, you know, what the topology of the space-time really is.
But that isn't the whole point. This global structure matters. That's the whole point of his talk, I guess.
Yeah, so I guess I'm just missing the point here. I mean, it's really, yeah, I mean, so why, for example, what happens at the physical scale of the pions have something to do with the, you know, whole space-time topology?
Whether you can define Wess-Zumino-Witten term well-defined way. Yeah,
yes.
well-defined way.
Yes, so we actually do not care at the actual physics, I would say.
Right. I mean, so you're trying to say, okay, yes, just as a mathematical problem, it's certainly well-defined and very interesting to study. But I guess my question is that, do you really believe, for example, what happens at pion scales? I mean, that, for example, the scales of pions really say detect something about the global space-time structure, or you think actually, you know, no, that's not the case. I mean, just on this more physical question, what is your standpoint?
In principle, this Wess-Zumino-Witten term should detect the global structure of space-time. Otherwise,
you think okay, that could be true. I mean, yeah, okay. I think that's that would be very interesting.
So that's the reason I asked what do you mean by local? So
I mean, just like on the scale of like a couple hundred capital M EV on that scale. I mean, so basically you're trying to say the physics on that scale really, I mean, the consistency of the physics on that scale, like, you know, 10 to the 8 electrovolts, really detect the global space-time structure, or really hinges on that.
It should.
Okay. I mean, yeah. I mean, I just want to hear your opinion on this. Okay, thanks. Yeah. As I said, I mean, sorry. Yes.
Yes, like for the SU2 case, you don't really have this Carroll anomaly, right?
No, right.
That's why you have this WZW term coming out. I think in Witten's original paper, this equation should be like exponential to minus x as would be the whole action, the whole QCD action, equal to this -1 to n stuff.
Are you asking,
Right.
well, is there an ordinary Wess-Zumino-Witten term NF equals 2?
Yeah, I mean, for just for the SU2.
Yes, in SU2, there's no ordinary Wess-Zumino-Witten term. There's only just, I mean, there's only possibility to, yes, only this term can enter, and there's no ordinary Wess-Zumino-Witten term.
I mean, the left-hand side of this equation should be just the whole action, right? Because there's no the whole as the action of the whole QCD, the action of the QCD.
No,
because there's no such a WZW term, right?
No, there should be kinetic term of sigma or whatever else. I mean,
yeah. This the left hand. The left hand side.
Right hand side. This one, right?
The left.
Left. Oh, sorry, left. Okay, left.
Yes. This one should be the whole action of the QCD.
So it's just a problem of notation, I think. So we just here denoted this term by using this symbol. I do not mean this WZW to be the full action of the low energy QCD.
Okay. Thanks.
Okay, let him move on first.
Sorry. So where did I go? Yes, I think I was doing the overview, I think. Yes. So okay. So next in the next part, I will review what this Bordism thing is, and then describe its connection to a special class of QFTs called invertible phases or invertible QFTs. And this modern point of view is actually the main motivation of this work. After that, we reanalyze the SU QCD and SO QCD, and then take further look at the novel aspects of SO QCD. So this is the plan of my talk. So there are two important notions to be explained. So one is the Bordism. Bordism group is an abelian group formed by equivalence classes of closed manifolds. So here, two d-dimensional manifolds, MD and MD prime, are defined to be equivalent if there exists a one higher dimensional manifold, WD plus 1, which connects them. Such MD and MD prime are said to be bordant. The operation we consider is disjoint union. So closed manifolds themselves form a monoid under disjoint union, where the identity element is an empty D-manifold. On the other hand, the equivalence classes of manifolds we defined form an abelian group under disjoint union, where the identity equivalence class is formed by closed manifolds bordant to empty D-manifold, or equivalently, closed manifolds which can bound a one higher dimensional manifold. Here, the group structure arises since for any manifold, its orientation reversal belongs to the inverse equivalence class. So this is a basic definition of the Bordism group, but one can easily extend this notion and further take various structures of manifolds into account. For example, if we take closed spin D-manifolds, MD and MD prime, and require the spin structure to be suitably extended across WD plus 1, the resulting group becomes a spin Bordism group. So in such way, so for our purpose, the structure we want to consider in addition to spin structure is the map from the manifold to the sigma model target space X. And this defines the relevant Bordism group omega d spin X. So that's the one notion. And the other notion we want to introduce is an invertible phase or invertible QFT. It is simply defined to be a QFT having one-dimensional Hilbert space on any closed spatial slice. One might think that such QFT is trivial, but actually that's not the case. And there can be non-trivial QFT having non-trivial partition function. These QFTs are invertible in the following sense. So given two QFTs, Q and Q prime, one can produce a new QFT by taking a product of partition functions and taking a tensor product of Hilbert spaces. Generic QFTs form a monoid under this operation, where the identity element is the trivial QFT with trivial partition function and trivial Hilbert space. However, for QFTs having one-dimensional Hilbert space, there always exists its inverse. So it is just the QFT with the inverse partition function and the dual Hilbert space, which is also one-dimensional. And that's why these QFTs are called invertible. So apparently, two notions introduced so far seem rather irrelevant to each other, but actually there's a deep, deep connection between them. So the recent understanding of the invertible QFT is that the group of deformation classes of invertible QFTs is captured by this following short exact sequence. Here, deformation just means the variation of the parameters. So two theories only differing in the value of the parameters are identified. As is shown, this group consists of two parts. One is the torsion part of the d-dimensional Bordism group, and the other is the free part of the d+1 dimensional Bordism group. So to see what kinds of invertible QFTs there are, we just need to calculate and determine these two Bordism groups. Having said that...
Sorry, I have one question.
Okay, sure.
Can you go back? So when you said deformation inverted QFT means so you just preserve the QFT needs to be invertible. So the Hilbert space is one-dimensional under deformation.
Yes.
Okay. And to be honest, I don't still understand this your definition invertible d spin of X. So you just consider d-dimensional manifold map to X?
D-dimensional manifold map to X.
And it consider QFT? Sorry, what's the definition? This red one? How do you define it?
It's I mean, so actually this is the definition, I would say, but
Okay.
it's roughly the dual of the Bordism group. So you can, so I introduced the omega d spin X before, and you can think of this as the dual, a certain dual of that omega Bordism group.
Okay, dual means under Hom or something?
Under what? Sorry.
Under Hom? When you say dual means...
Hom. So yes. So this is the usual Bordism group, and in this way, one can define something called Anderson dual.
Okay, Anderson
and this
dual.
is the the object. But yes, you can. I think you can roughly. You can just think of it as some cousin of Pontryagin dual. I mean, yes, Pontryagin dual. So yes, like Hom. Okay. This Hom Bordism to U1 or yes.
Okay,
like
I see. Okay, thanks.
Thanks. Okay. So we want to know how to calculate these Bordism groups. So, but this calculating Bordism groups is usually a very, very difficult task. But thanks to mathematicians, there are powerful exploitation tools called Atiyah-Hirzebruch spectral sequence and Adams spectral sequence, which enable us to extract partial information on Bordism groups, and sometimes even allow to fully determine the desired Bordism groups. I will not explain any detail in this talk, but one can think of these as black boxes, which take certain homology groups or cohomology groups of target space X as input and return Bordism groups as output. So in the next section, we will revisit the Wess-Zumino-Witten terms in SU QCD from this modern Bordism point of view, and see that they can actually be described as spin invertible phases. So first, let's see what's going on in the NF larger than or equal to 3 case. The relevant Bordism groups can be calculated from this strange diagram above, which you can completely ignore. And these two are the results. So first, this 4-dimensional spin Bordism group is trivial. Recalling the story in the introduction part, one of the concerns we had was that the auxiliary 5-manifold W5 used in the definition of Wess-Zumino-Witten terms, which is bounded by the spacetime 4-manifold M4, might not exist. In such case, we still have a chance to be saved if the W5 connects M4 to another 4-manifold equipped with trivial sigma configuration. Here, this 4-dimensional Bordism group exactly detects whether it is possible to do so, and it being trivial means that the answer is yes. In other words, so for any spacetime manifold M4 equipped with sigma configuration, one can always find either a bounding W5 or W5 connecting to another 4-manifold equipped with trivial sigma configuration, with this sigma consistently extended to W5. So we have successfully fixed the problem number 1.
Sorry, could you remind omega tilde? What tilde is?
Yes, omega tilde is actually the subgroup of full omega, which is sensitive to this sigma part. So there is completely, purely gravitational, and there's a part which is completely independent of sigma, and we modded out that part, and that's the omega tilde.
Okay, what's the first problem you fixed now?
So yes, so so sorry. So you have, should I say? So you have spacetime M4, and there might be, sorry. Okay, so there might not exist such W5 in the first place. I mean, let's see, so it'll be explained in the NF equals 2 case, but let me be brief. So, so for given M4, you might not be able to find a 5-manifold bounding M4.
It's like K3, you mean?
Yes. Okay. It's like K3. But this group being trivial means that you can always find such bounding W5 or connecting W5 to another 4-manifold with trivial sigma configuration.
I see. How about second line? What does second line mean?
Yes, this second line, this 5-dimensional spin Bordism group equals Z, and this is twice the 5th homology group of Z. And this factor 2 cures another problem in the introduction part.
Which one is another part? This 1/2 or something, you mean?
Yes, another problem is this, yes.
I see.
Yes, yes. Again, so recalling the story in the introduction part, this gamma phi integrated over generic closed phi manifold might not be an integer, but a half integer, right?
Okay, I see.
And yeah, that was another problem we had defining the Wess-Zumino-Witten term. Yes, but
That
this
depends on whether the manifold is spin or not.
yes, 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 that's right. Yes.
Yes.
So if this phi manifold can be equipped with spin structure, then the calculation of Bordism group implies that the integral over such spin phi manifold
Mhm.
takes value in the twice the integral over generic phi manifold, since the Bordism group is twice the homology group, which
Okay.
is namely, yes, which is namely integers in this case.
Okay, I understand. Thanks. Please go ahead.
Thank you very much. Yes, twice the half integer is the integers, yes. So therefore, one can see that the Wess-Zumino-Witten term is well defined on generic spin phi manifolds, since the difference between two Wess-Zumino-Witten terms becomes 2 pi I times an integer, not a half integer. And correspondingly, the exponentiated action does not depend on the way of extension. So for NF larger than or equal to 3, two Bordism groups we saw nicely describe the ordinary Wess-Zumino-Witten term. So next, let's look at the NF equals 2 case. So again, relevant Bordism groups can be calculated from this similar looking diagram as before, but this time the result is rather different. The 4-dimensional Bordism group is not trivial. So this means that, so I said earlier, but so generic M4 equipped with generic sigma might not be able to be connected to another 4 manifold equipped with trivial sigma. In this case, to determine the value of the Wess-Zumino-Witten term for generic M4 and sigma, we first have to pick a representative of the equivalence class to which it belongs, and fix what value to take for Wess-Zumino-Witten term on that representative pair of boundary 4 manifold and sigma on it as an anchor. Then the natural definition of the desired Wess-Zumino-Witten term for original M4 would be this fixed boundary value on the representative 4 manifold times the ordinary Wess-Zumino-Witten term on W5, connecting M4 and this representative 4 manifold. And when NF equals 2, there was no ordinary Wess-Zumino-Witten term, so the value of the Wess-Zumino-Witten term for original M4 is equal to that for representative 4 manifold. So which means that it only depends on the Bordism class. So in other words, for any two 4 manifolds equipped with sigma configuration belonging to the same Bordism class, the value of the Wess-Zumino-Witten term should be the same. And it turns out that this freedom or ambiguity in fixing the value for the representatives exactly corresponds to the choice of weight on non-trivial sigma configuration, which is namely the discrete Wess-Zumino-Witten term. So things are getting complicated, so let me explain it in more detail. So the 4-dimensional Bordism group was Z2, and this means that a generic 4 manifold M4 equipped with sigma belongs to one of the following two equivalence classes. They can either be connected to another 4 manifold equipped with trivial sigma configuration, or it can only be connected to another 4 manifold equipped with non-trivial sigma configuration, which cannot be smoothly deformed to trivial configuration.
So when you say here sigma is spin structure or map?
Sorry, it's a map.
Okay.
Sigma is always a map.
Okay, sigma is always map. Okay.
In this talk.
Okay. But sometimes you use sigma as a spin structure? No.
No.
No, okay.
Yes, you can think of sigma as a map. In this talk, yes. So on this side, so one can just demand the Wess-Zumino-Witten term on the other side here to be 1, since the sigma configuration is trivial. Then the desired Wess-Zumino-Witten term for this spacetime M4 is given by 1 times the ordinary Wess-Zumino-Witten term on W5. And since the ordinary Wess-Zumino-Witten term was absent for NF equals 2, the product is 1 times 1 equals 1. So for M4 equipped with sigma, which belongs to this side, so everything is trivial and nothing happens. On the other hand, on this side, there's some freedom to choose the value of the Wess-Zumino-Witten term on the other boundary. So since the Bordism group was Z2, it should be order 2. So the possible value to take is +1 or -1. And choosing -1 here corresponds to weighting the non-trivial sigma configuration in the fourth homotopy group we saw, since the fourth sphere equipped with non-trivial sigma happens to belong to this non-trivial element of the Bordism group. So let's recap what we saw in this section. So recall that we had this short exact sequence. For NF larger than or equal to 3, the torsion part of the 4-dimensional spin Bordism group was trivial, while the free part of the 5-dimensional spin Bordism group was Z, which described the ordinary Wess-Zumino-Witten term. On the other hand, when NF equals 2, the ordinary Wess-Zumino-Witten term did not exist. So I haven't mentioned in the slide, but the free part of the 5-dimensional spin Bordism group turns out to be trivial. And this reflects the absence of the ordinary Wess-Zumino-Witten term. Instead, as we saw, the torsion part of the 4-dimensional spin Bordism group becomes Z2, which corresponds to the existence of discrete Wess-Zumino-Witten term. And as a whole, this ordinary and discrete Wess-Zumino-Witten terms can be viewed uniformly as a spin invertible phase. The similar analysis can be carried out in SO QCD. So let's see. Is the sound of ambulance in this? Ah, sorry.
Yeah. I heard a sound of ambulance several times in this talk.
It seems the hospital is busy, so sorry.
Okay.
Let me just wait a little.
Don't worry. Go ahead. It's not that big deal.
Okay, thank you. Then let me continue. So SO QCD is an SONC gauge theory coupled to NF Weyl fermions in fundamental representation of the gauge group. In SU QCD, we had to include additional NF anti-fermions in order to cancel the gauge anomaly. But in SO QCD, since the fundamental representation is real, not complex, there's no distinction between fermions and anti-fermions, and also there is no gauge anomaly. Therefore, the flavor symmetry of SO QCD is just SU and F, which acts on Weyl fermions. Similarly, in the IR nonlinear sigma model, bilinear condensates formed by fermions is only invariant under SO and F subgroup, and the sigma model target space becomes SU over SO. Again, there is a tooth anomaly of the flavor symmetry in the UV for NF larger than or equal to 3, which is matched in the IR by slightly different Wess-Zumino-Witten term. This time, it integrates to 1/4 on generic closed 5 manifolds. So one can compute the Bordism groups as in the SU QCD case, and the 5-dimensional spin Bordism group turns out to be Z, which is 4 times the 5th homology group, and therefore the ordinary Wess-Zumino-Witten term is guaranteed to be well defined. So 4 times 1/4 is the integers. However, this time the 4-dimensional spin Bordism group is not trivial, and there is ambiguities in the values of the discrete Wess-Zumino-Witten terms even in the NF equal larger than or equal to 3 case. In principle, these discrete Wess-Zumino-Witten terms in the IR should be uniquely determined from the UV QCD, but it's almost hopeless to carry out a path integral. We haven't managed to decide which choice is actually realized. So if you are interested, we'll see also Yonekura-san's paper, which discusses this issue. So far, we have reanalyzed SU and SO QCDs, but for SO QCD, there's additional interesting story involving novel symmetry and the anomaly associated to it. So I will discuss this novel anomaly and its matching for the rest of the talk. And from now on, we take the number of colors to be even. So we consider SO2 and CQCD. In these cases, as I will explain later, QCD can actually be put on non-spin spacetime manifolds, even though the theory contains fermions. Of course, this does not come for free, and it gives rise to the mixed tooth anomaly between two symmetries of the theory. One is the ordinary zero-form spacetime spin symmetry, and the other is the Z2 one-form magnetic symmetry, which I will also explain later. So when we put the theory on non-spin manifold, an attempt to gauge both of these symmetries fails, because the theory cannot be made gauge invariant. So by the way, although I won't discuss this in this talk, there's something called two-group symmetry in spin QCD as a counterpart of this, which again involves the non-trivial mixing between zero-form and one-form symmetries. But anyway, so we had this mixed tooth anomaly, and as always, we expect this mixed tooth anomaly to be reproduced in the IR. And in fact, it turns out that the Wess-Zumino-Witten term is responsible for this anomaly matching. In short, the Wess-Zumino-Witten term on non-spin manifold is actually well defined at first for even colors, but when we gauge both of these symmetries, it becomes ill-defined. And this signals the impossibility of gauging, which is exactly the mixed tooth anomaly. So that's the rough story. So let me first explain why the theory can be put on non-spin manifolds when the number of colors is even. So first, consider which symmetry charges the fermions. By definition, they are of course charged under spacetime spin symmetry, and also there are SO gauge symmetry and SU flavor symmetry. However, if we carefully examine the action of these symmetries, one notices that -1 to the F at a fermion number in the spacetime spin group and -1 in the gauge SO group act in exactly the same way. So therefore, fermions are actually charged under Z2 quotient of their product. This means that we actually have SO spacetime symmetry times SO over Z2 gauge symmetry at first. And this, whether this spacetime SO lifts to spacetime spin is synchronized with whether gauge SO over Z2 lifts to gauge SO. As a result, the theory can be put on non-spin manifold if we suitably take corresponding non-trivial gauge bundle. So let me rephrase this in more. Yes.
It's very similar to spin C bundle.
Yes, it's very similar to It's
instead of U1, you just take
SO2.
SO2 and
yeah. For NC equal 1 case, it's just spin C.
Yeah, spin C, right? Okay. Thanks.
Yes. Yeah, it's just the generalization of the spin C. Yes, you can think of it like that. Yes. So let me rephrase what I said in one more concrete way. So obstructions to the lift of bundles are captured by certain characteristic classes. For our case, whether spacetime SO lifts to spacetime spin is known to be controlled by Z2 valued characteristic class W2 of the tangent bundle, while whether gauge SO over Z2 lifts to gauge SO is known to be controlled by another Z2 valued characteristic class V2 of the gauge bundle. Here, a manifold being non-spin is actually equivalent to the manifold having non-trivial W2. So if we take this V2 to be equal to this non-trivial W2, then one can put the theory on non-spin manifolds. So that's the trick. And let me describe these characteristic classes in more detail. The relevant cases are these two cases. And for the spin 4n group, center is known to be Z2 times Z2, and correspondingly, there are two independent cohomology classes, V2 and W2, both Z2 valued. Starting from SO over Z2 bundle, one can lift it to SO bundle if the V2 is trivial. And if further W2 is trivial, it can be lifted all the way to the spin bundle. On the other hand, for spin 4n plus 2 group, center is known to be Z4. And correspondingly, there are two cohomology classes, X2 and V2. This time, this X2 is Z4 valued, and V2 is a mod 2 reduction of this X2. So it is Z2 valued. Again, starting from SO over Z2 bundle, one can lift it to spin bundle if this X2 is trivial. But even when this X2 is not trivial, one still has a chance to lift it to SO bundle if the V2 is trivial, or equivalently, if the X2 is trivial mod 2. So furthermore, one can define an object corresponding to W2 on this side too. But it turns out that there's a non-trivial relation between this W2 and the V2, as opposed to the spin 4n case on this side. So for 2 mod 4 case, so all the information are encoded in the short exact sequences called chain groups, induced from another short exact sequence above. So where this Z4 is the center Z4 of the spin 2 mod 4, and this Z2 right on the right is the mod 2 reduction of this Z4. So I won't explain any details, but there's so-called connecting homomorphism, which takes this V2 to delta W2. And this is the beta here. So beta takes V2 to delta W2. And it is called Bochstein homomorphism. So the beta is for Bochstein. And as one can read off, this W2 here, the object we are trying to define, is not a cocycle, but a cochain in general. And it becomes cocycle only when the V2 is trivial. And hence the SO bundle is actually realized. So if we can lift the original SO over Z2 bundle to SO bundle, then W2 can be turned into a cohomology class and serves as the ordinary class governing the further lift to spin bundle. But one can completely forget about these details, but just remember that there's such non-trivial relation between the characteristic classes controlling the lift of each bundles for 2 mod 4 case, so spin 4n plus 2 case. For the 0 mod 4 case, there's no such relation, and W2 and V2 are completely independent. And with this, we are finally ready to analyze the mixed tooth anomaly. So let's start from the UV side. So in the SO QCD, there's a tooth magnetic flux, since the gauge group SO2 and C is not simply connected. So the fundamental group of SO is known to be Z2, for large enough NC. The magnetic flux is characterized by this degree 2 cohomology class W2, which is the same W2 as that we saw in the previous few slides. As it controlled whether the gauge SO bundle lifts to spin bundle, it indeed measures a certain non-triviality of the gauge SO bundle. Our interest is in that this W2 defines a 2-dimensional surface, which corresponds to the world sheet of magnetic flux tube attached to the magnetic monopole. In this sense, this is called one-form symmetry, which charges a 1-dimensional flux tube, by analogy with ordinary zero-form symmetry, which charges a 0-dimensional particle. As we all know, for a charged particle, one can couple it to one-form gauge field A. Similarly, for a charged string, one can consider coupling it to 2-form gauge field B. So the coupling can be written like this, but there's one problem. So if we implement gauge transformation, this term might not be invariant. So let's see what I mean. So under the gauge transformation, this 2-form gauge field B is sent to B plus delta lambda, where the lambda is the ordinary gauge transformation parameter. And by partial integral, this coboundary operator here hits this W2. Recall that since we are considering the theory of non-spin manifold, what we actually have at this point is an SO over Z2 gauge bundle. And there was a non-trivial relation between W2 and V2, W2 and V2 here, for 2NC for 2 mod 4, or equivalently odd NC. For even NC, 2NC is 0 mod 4, and there was no such relation, and delta W2 automatically vanishes. So that's the first point. And furthermore, by putting the theory of non-spin manifold, this V2, C, which controls the lift of SO over Z2 bundle, was said to be equal to this W2T, which controls the lift of spacetime SO bundle, as we saw before. As a result, this coupling alone is not Z2 one-form gauge symmetry invariant, and its non-invariance is related to the zero-form spacetime symmetry. In this sense, two symmetries have mixed tooth anomaly and cannot be gauged simultaneously. To cure this, we have to add bulk 5D action of this form, which suitably cancels the anomaly on the 4-dimensional boundary. And that's the story in the UV. Next, let's see what's going on in the IR. So first of all, we are curious whether there's Z2 one-form symmetry, or equivalently Z2 charged strings. And in fact, there is, which can be seen from the second homotopy group of the sigma model target space. So as written in this box, for NF larger than or equal to 3, this pi2 of SU over SO is known to be Z2. So we expect the mixed tooth anomaly in the UV to be somehow reproduced in the IR. But meanwhile, recall that there was a Wess-Zumino-Witten term for NF larger than or equal to 3. On spin manifolds, there was no problem at all in defining it, but since we are on non-spin manifolds now, one should worry that this might make the Wess-Zumino-Witten term to be ill-defined. On generic 5 manifold, the gamma 5 might integrate to 1/4 for the worst case. Since we took the number of colors to be even, one can save the factor 2. And for even NC, one can save another factor of 2 and problem is solved, since 1/4 times 2 times 2 equals 1. But for odd NC, this still does not guarantee the integrality. So let's check explicitly whether it integrates to integer or not, means half integer. And for the convenience, we will compute 4 times gamma 5 and check whether it integrates to even integer or odd integer. So for the Wess-Zumino-Witten term to be well defined, we want this 4 times gamma to be integrated to an even integer. By carefully examining the cohomology of the sigma model target space SU over SO, one can compute 4 times gamma 5 mod 2 as follows. Here, these W2 prime and W3 prime are the Z2 cohomology classes of SU over SO. But anyway, so after some computation shown in the slide, we end up in this form, which is exactly the bulk 5D action we needed to add in the UV to compensate the mixed tooth anomaly. So it is obvious that if we have not gauged the one-form Z2 symmetry, or in other words, if we have not turned on the two-form background gauge field B, then the right-hand side is 0. And this means that 4 times gamma 5 is 0 mod 2, which means that it is indeed an even number. And Wess-Zumino-Witten term is safely well defined. However, when we gauge the Z2 one-form symmetry, new bulk 5D action arises from this Wess-Zumino-Witten term, which is exactly what we had to add to cure the mixed tooth anomaly in the UV. And this is how the novel anomaly in the UV is matched in the IR by the Wess-Zumino-Witten term. And that's the end of the another story. So let me briefly summarize my talk. So there are 2 claims I wanted to convey. One is that the Wess-Zumino-Witten term is actually a spin invertible QFT. It can be neatly described from modern Bordism point of view. The other is that there is novel anomaly in SO QCD, and it can be matched by Wess-Zumino-Witten term in a quite interesting way. And that's all. So I'll stop here. Thank you.
Thank you very much. Questions?
So one of the physical point that I just want to ask if you agree or not is that basically what you have shown is that essentially how the symmetry patterns breaks as you go from the UV to the IR actually is independent of the topology of the whole space-time, because in all the cases possible, in all the cases that you have considered, it is possible to construct a WCW term that in the IR that always matches the associated anomaly in the UV, right? So it's really, I mean, from the physics side, what you would say is that the topology really does not, say, affect the symmetry breaking patterns of the QFT.
No.
You agree with that, right?
No.
It does not. Oh, okay. Okay. You just want to make sure.
Other questions?
I have a question. The W term, if I differentiate it, it's proportional to the Chen class, right? Like the gamma 5 stuff.
Which part are you talking about?
I'm just I just want to ask some general property for the gamma 5. The gamma 5, the WZW term. So if I take derivative with respect to sigma on this gamma 5, it should be proportional to the third Chen class.
Right? So yes, the D gamma 5 should be equal to the third Chen class, right? Yes.
Yes. So, but what about gamma 5 itself? It corresponds to some certain characteristic class or not?
So the Chen class is in the cohomology class of the BG, right? I mean, the classifying space of the gauge group G, right? The sort of symmetry group G. But the Wess-Zumino-Witten term is in the cohomology class of the symmetry itself, G. So H5G. The Chen class is in H6 of BG. And yeah, they are actually, I mean, intimately connected by, should I say, I intentionally did not write that in this talk slide, but yes, there is indeed a connection between the gamma 5 and the Chen class. Yes.
Oh, okay. No, my question is more like, for example, the D gamma 5 integrating over the D gamma 5 is like the sixth form, right?
Yes.
If I'm integrated over the sixth manifold corresponding to the third Chen class of the sixth manifold. But gamma 5 itself integrating over this five-dimensional manifolds give you some like characteristic class of the 5 manifold itself, like the spin structure of the 5D stuff. If I understand correctly, then does this gamma 5 itself is also some like a topological characteristics?
I'm not sure what are you meaning by the top. I mean, it is top. I mean, it is certain topological class, right? I mean, are you asking, is this gamma 5 has any special name or something? Are you asking that?
Yeah, something like that, right? In mathematical.
To my knowledge, no. I don't think this gamma 5, I mean, the class corresponding to gamma 5 has special name or something like that, but it is the topological class of the manifold, yes.
Okay. Thanks.
Any other questions?
I'm ignorant, but is there any role if you have non-trivial theta term like theta equal to pi? Is there a change of story or?
Theta angle.
Yeah, theta angle.
Yes. So if the theta angle is yes the crucial point. Yes. So if you, so I said, where is the slide? Let's see. Here. So yes, I said that we haven't managed to determine the discrete Wess-Zumino-Witten part, but so if you fix the discrete theta or continuous ordinary or discrete theta angle in the UV, so it should uniquely determine the discrete Wess-Zumino-Witten term in the IR. Yes. And the Yonegra-san's paper argues that, yes, certain choice of theta angle in the UV should correspond to certain choice of the discrete Wess-Zumino-Witten in the IR.
Okay, thank you.
Other question from audience? Okay, if not, let's thank the speaker again.
Thank you.
So I will switch off the recording. I'll leave the space for informal discussion.